All right, great. Good. So this is not a good example of what I was starting off with, but this is the way. This is at least it's an example of showing you how shortest paths can arise in scenarios where you really are looking for paths with certain different kinds of weights. Okay. Let me give you another example where actually negative weights do come up. So let's suppose I give you So let's suppose I give you a directed acyclic graph. Okay, and I asked you to find the longest path, and it has weights, and I asked you to find the longest path. Okay. In general, finding longest paths of graph is one way to try to do it. Is what we do. You make all the weights negative, and then you apply shortest paths. Right? So one way to find longest path is negate all the paths, negate all the weights, and run shortest paths. Okay? You agree that if you negate all the weights and you run shortest paths, then shortest path in the graph with negative weights, is what it was before, would be longest path of the original graph. Okay? But if you were to do this, we cannot run Dijkstra because Dijkstra doesn't apply to negative weights. You can apply the other algorithm, doesn't fork. Okay. This is also not a great example because for directed acyclic graphs, you can do it faster than running Bellman-Ford. You can do it in a different way. But why did I say directed acyclic graph? Was because remember, if you allowed cycles and if you have negative weights, then you could have negative cycles. Then no algorithm will likely work if they have negative cycles, because if you have negative cycles, then paths are not well defined. Shortest paths are not well defined. Okay. So, but there are many scenarios where you do want to work with negative weights because the weights do not necessarily represent distance; they represent something else. In those cases, you do need. Okay, so Dijkstra's algorithm works in theta and log n. If you remember that. The other algorithm that we saw was Bellman-Ford. That works in time theta and n. Okay, remember how it worked? It just went through every edge went through every edge, fixed distances, and just repeated doing it at least n minus 1 times, and it ran it n times n. Okay. One other advantage, so it works for negative weights. It allows negative weights. One other very nice advantage of it was it discovers negative weight cycles if they exist. Okay, that's very useful to know. So you should go. We didn't spend a lot of time looking at that, but you should just review that and make sure that you understand how Bellman-Ford's algorithm discovers negative weight cycles. Okay, good. So we have that. But all of this is from a single source. Bellman-Ford is from a single source. Dijkstra is from a single source. Let's suppose we were to apply that to all pairs. Okay. So what is one way to solve all pairs? So let's look at all pairs shortest paths. One solution is run Dijkstra from every source. Okay, this would be a valid solution if you assume that the graph has no negative weights. Okay, what will be the running time of this algorithm? M and log n.
Professor, I have a question.
Yeah.
Does all pair shortest path mean that like from every node to every other node?
Yes.
There's a shortest path?
Yes.
But then Dijkstra, as like you don't know if each path from a different node from Dijkstra is gonna end at a different location though.
No, when you run Dijkstra's, it finds the shortest path from the source to every other vertex. Because remember, it builds this shortest path tree,
Oh.
and it stops when it's finished shortest path to every single vertex. Yes.
Do we need to run it from every source or every vertex?
Well, every vertex is a source. So, yeah, it means from every vertex as source. Okay? Right? Okay, so that's one. Run Bellman-Ford from every vertex. That's another option. This will work even when there are negative weights. Okay, it will not be, if there are negative weight cycles, then it will complain and stop, or you can let it do whatever it wants. But if you, so that this takes theta mn square. Okay. Now you realize the running times of these algorithms. If you're talking about n as a million, as we just mentioned, n as a billion, this is sort of prohibitively large. Okay, this is like more than a trillion, and this is huge. It's like 10 to the power 18 or something. So that is why solving all pair shortest paths is so critical, because you are often looking at really large graphs. Even with million vertices, million edges, it becomes basically perfect. Okay, so we are going to look at trying to beat these bounds. Maybe not certainly by certain amount. The other thing you notice that the running times are now so large that, remember, until now we have always been thinking of as the graph has been given to us in the form of an adjacency list. Why is that? Because adjacency list just basically is the most efficient way of getting it. If you give an adjacency matrix, it's an n cross n matrix that already takes n squared. And if n is not large, n squared could be large. But remember, here we are already talking about times that are much n squared or bigger. Okay? So in all pair shortest path, since we are looking at all the pairs, we have to spend at least n squared time, right? Because for every pair we have to give some answer. So for all pair shortest path, it's much easier to think about the input being given as a matrix. This is the weight matrix. Okay, so you're given a W, a weight matrix, which has a weight 0 along the diagonals, indicating every edge vertex to itself is a 0. And everything else, if you look at the ith row and jth column, you have the weight Wij. What does weight Wij mean? That's the weight of the edge going from I to j. Okay, so that's the input. All right? Okay, good. So now that's the input, and the question is, give me the best way to get find the shortest path. Okay. So finally, so let's try to think. Then we will come up with a couple of different algorithms. So the first algorithm to observe is, notice that W itself, the matrix Wij, is the weight of shortest path from I to j using at most one hop. Okay, so let me remind you of what this weight matrix is. It gives you the weight of the edge going from I to j. What if I did not have an edge to j? What should be set its weight to be equal to? Infinity, because remember we're looking for shortest path. So its weight is Wij if there is an edge from I to j. That's the weight that's here. If no edge, Wij equals infinity. Okay? Okay, good. So you agree that the weight Wij is the weight of the shortest path from I to j using at most one half. Okay? So let's try to see whether we can build on this observation. So let's say I define Cijk. Let Cijk, there are three variables, okay? You can see where we are heading. We are heading, trying to write a dynamic program. Let me define Cijk equals weight of shortest path from I to j using at most k hops. Okay? You know what the meaning of at most k hops is? You're allowed to go in at most k steps, going from I to j. Okay? All right? Yes?
I'm not sure how you can have, okay, sorry. One hop
Yeah.
is only relevant if you have multiple paths from one vertex to another of different weights. Don't we not have multiple?
No, so can you explain again? So let's say there is, let me draw an example of the graph. Okay, so let's say
Okay. Right, so in this situation, you don't have to do any calculations. Just find if there are any paths from either j or one hop. There's no.
correct. So in this case, what is Wij?
6.
Correct. So if I want to find the shortest path from I to j using at most one hop, I agree there is nothing to do.
Okay.
It's just whatever the weight matrix was given to us.
Okay, sorry.
But the one I'm interested in is the shortest path from I to j using at most k hops. That's what I want to help. Okay? So what is the shortest path from I to j using at most 2 hops? 5. What's the shortest path from I to j using at most 3 hops? 4. What is the shortest path from I to j? 4. So if I keep doing this for 1 hop, 2 hops, 3 hops, k hops, how many hops should I consider?
N minus 1.
Maximum I have to consider is n minus 1. Because assuming there are no negative weight cycles, my shortest path will never have more than n minus 1 hops. It could have far fewer than n minus 1 hops, but it's never going to have more than n minus 1 hops. Okay, so the idea is going to be, so let's continue with this. So let's try to figure out how to calculate Cijk. Okay. So I have to go from I to j using at most k hops. Okay. Let's suppose this is I. Okay, so what I would like people to do is try to write a recurrence for this by yourself. Okay. Let me. What's the base case? This k equals 1. So what is Cij 1?
It's either equals to Wij or equals to infinity.
Right. Well, Wij we already decided was either going to be the weight of the edge or it's going to be infinity. Okay. So Cijk is equal to Wij if k equals 1. If k equals 1, it's the weight of the edge ij, which we have decided it will be if the edge exists, it's the actual weight of the edge. If the edge does not exist, that's equal to infinity. Everybody agrees with that? Okay. So if k is not equal to 1, how do I figure out what is the shortest path from I to j using at most k hops? Okay. So the trick is to look at either the first hop out of I or let's say the first hop into j. So let's say these are all the vertices that have edges into j. Okay. What can you say about the shortest path from I to j using at most k hops? And let me put some things here: A, B, C. Okay. So let's see. Everybody should try to give it a shot. I think at this point you should be able to write from shortest path from I to j using at most k hops. Can you express it in terms of going from I to A? Okay, if you have a shortest path that goes from I to j using at most k hops, it contains the shortest path from I to A using at most k minus 1 hops. So what will this be? Cik k minus 1, and then you have to go from A to j, which is just the edge of the edge. Okay. Of course, you do not know whether it's A or B or C or D. So what will you do? You will take the minimum of all of these choices. Okay. Okay. So let's use a variable for the last hop. So what variable do you want to pick? We already used k, so let's say L. Let's say L is the previous variable. So you're going from I to L using k minus 1 hops. So Cil k minus 1, and then you're going from L to j using just 1 hop, whose weight is WLJ. Okay, and what are you doing? You're taking the minimum over all choices of L. That's basically it. And L can be any value. It doesn't, I mean, here I showed you only those that have edges into it. But remember, if there are no edges into it, you will just have infinity. So you just take L to be all possible choices. So this is a dynamic program for all pairs or path. And the way dynamic program here works, it first considers how will we run it. We will first do one hop, that's easy. Then you will do 2 hops, which is you will just run this whole thing one round, then 3 hops, then 4 hops. We'll write this as a piece of code momentarily. But is it clear? What's going on? Yes?
How do you know where K stops on the algorithm?
So K, good question. So the point was that if you look at the shortest path from any 2 vertices, it should not contain more than n-1 hops. Because unless there are -8 cycles, but we are assuming that there are no -8 cycles. Okay? There is no point in having a cycle in your path. So if there is no cycle in your path, then every vertex is distinct, so you have n-1 hops. So you will run it for exactly n-1. Okay. One other thing notice is this is only calculating the cost. We always have the standard problem. How do we extract the actual solution? And it's the same thing. We will keep track of which of the L's actually give you the minimum. And so we will have another variable called, let's say, pi ijk, which will store that L that give you the minimum for ijk. Okay. All right, let's keep going. That's up. So I can write this out as a piece of code like this. So we will have this array C, I, J, L. That would be our array, 3-dimensional array. So first we will set Cijk, sorry. Cijk. So I'll say for I equal to 1 to n, for j equals 1 to n, we will set Cij1 to be equal to Wij. Remember, W is the input. We are given this as the input matrix, right? The weight matrix. And now I simply run that. So this has set up the base case. Okay? So then I do for I equals 1 to n, for j equals 1 to n, for k equals 1 to n minus 1. Okay? What do I need? Now I need to take the minimum over all L. So I need another loop, right? For L going from 1 to n, and then I have to pick the minimum. Okay, let me try to expand that just so that. So I will say initially, let's say I keep track of this thing called min equals, I set that min to infinity because I'm going to bring it down. So for L equals 1 to n, if min is greater than C I J, sorry, C I L K minus 1, plus WLJ. Okay, what I'm going to do is, min is storing the current minimum value that I have. Remember, I have to take the min of n values, right? Min is storing the current minimum value. I check to see if it is greater than what I need to compare with, CILK minus 1 plus WLJ. If it is greater, then what do? We change the min. Then we change the min to be equal to CILK minus 1 plus WLJ. Okay? And at the end, what do? After this for loop, we have computed the min. So we set Cijk to be equal to that min. So that's it. So once we have done that, what do you return? So Cij n minus 1 contains the shortest path. Okay? Yes?
Why does ij n minus 1, why does n minus 1 particularly come from?
N minus 1, remember k equals n minus 1.
Oh,
That's the n minus 1 hops. So that's the last value that I have. Okay? Now, if we had to get actually the path itself, what would we do? We will, whenever we change the min, we will change the corresponding last hop. So let's call it, let's have an array called Lijk. Lijk stands for the previous, or maybe let me say, it's the last hop. The vertex, that was the last vertex, the A, B, C, D, which vertex gave me the shortest path? The last hop in shortest path from I to j using at most k hops. Okay. So at this point, when you change the min, what do you change your Lijk to? To L, because L is the thing that is giving me the best value right now. Okay. Okay. By the way, we could have avoided using min at all. You could have just put Cijk to be infinity, and we could have just changed the Cijk here. Okay. And how do we get back the shortest path then? Well, we find the last hop, and then we go and look in that table for its last hop. And we go and look in that table in this last hop, and then we keep going. Okay. Okay. By the way, one thing I just said, I should have made sure that I made one mistake. There is one mistake in the recurrence. There is another base case. What is the other base case that we forgot? CII. What is CIIK? 0. So we should make sure that we set that to be. So we should also make sure that that's the case here. That for all I equals 1 to n, for all k equals 1 to n minus 1, CIIK. Okay, we should fix this accordingly. Okay? What's the running time of this algorithm? Okay, look at this algorithm carefully and say what the running time of this algorithm is. It's just a bunch of for loops. So you have an n here. Sorry, you have an n here. This is a different same level. Okay, you have something here. You have an n here. What do you have? N. What do you have? N. What do you have? N. So what's the running time of this? N to the 4. Okay? So you have your algorithm whose running time is N to the 4. And you're supposedly coming up with a better algorithm. Dijkstra's algorithm, which I have erased it, was only m times n log n. How large can m be? N square. So that's only n cube times log n. Okay, cube times log n. Of course, it doesn't work for negative 8s, but certainly better than n to the 4. Okay. So let's see whether we can do something with this. Okay. So here is a very interesting observation you can make out by looking at. So look at that definition here. It says Cijk equals minimum 1 less than equal to L less than equal to n of CIL k minus 1 plus. Okay? That is the main operation we are doing. You agree? That's all we are doing repeatedly in everything. Okay. And of course there is the base case system, but let's just focus our attention on this particular one. Okay. So let's look at this in the following manner. So what is this? This is a matrix, right? This is your weight matrix. You agree that this is another matrix. CIL k minus C k minus 1 is another matrix. Okay. Okay. So let me do the following. Let's so this is one matrix. Let me write this first. A C Ij so I have this weight matrix. Okay, and I have this C k minus 1 matrix. C k minus 1 matrix. Okay, and this is my weight matrix. In order to calculate the ijth entry of my new matrix, what am I doing? I'm going through all values of L between 1 and n, and I'm taking C, so let's say this is row number I. So I'm looking at row number I, I'm looking at L equal to 1, L equal to 2, L equal to 3, L equal to 4, and so on, until L equals n. And I'm looking at the weight, the nth column here. So I'm adding these two numbers. So this with this. And then I'm adding these two numbers. This with this. And I'm adding the next two numbers. And I'm taking the minimum of those. Okay? So again, what are we doing? This plus this. This plus this, this plus this, this plus this, and I'm taking the minimum of all of those. Okay? Is that clear? Okay. I'm calculating, how many sums am I calculating? N sums, and we're taking the minimum of all those n sums. Okay. So I'm taking a row and a column, and element by element, I'm adding and taking the minimum of this. Okay? This should remind you of very similar to what we would do with matrix multiplication. How do you multiply two matrices? You take a row of a matrix, you take a column of the other matrix, and what do? You take the first element, and what do you do with the second element? The first element here, you multiply. Then the second element here, with the second element here, what do you do again? Multiply. So you multiplied element by element, and then you add them up. What are we doing here? We are adding element by element and taking the min. But fundamentally, they are basically the same thing. Okay, I mean it's the same thing as if we were to replace multiplication by addition and summation by min. Okay, it's of course it doesn't matter. You can take the same code that you wrote for matrix multiplication. Wherever you are adding, you could have replaced that by min, and wherever you are multiplying, you could have replaced that by addition. And exactly the same thing would work here. Okay? So that's an observation. So basically what we are saying is that all price shortest path is equal to the same thing as you start off with your matrix W. Okay? So let me do that. Okay, so let's try to. So what is Ci when we are calculating C2? Okay, we are taking the matrix for C1 and multiplying it in a funny way with the matrix W. Right? You agree? What is C1? The shortest path from I to j using at most one half. What is that? W. So C2 is nothing but taking W, multiplying with itself in a funny way. And what is this funny way? Replacing product by summation, replacing summation by min. Okay? So what do you think C3 is? It's W times W, that is C2 multiplied by W. Okay? And what is C to the n minus 1? W times W times W. Okay? So essentially that's all we are doing. We are raising the weight matrix to a certain power. Except this is a very funny multiplication. It's the multiplication where we know what the replacements are. Okay? This is literally W to the power of n minus 1, where by powering we mean we are multiplying in this different notion, more abstract, different abstract notion. Very good. Okay, so far you're with me? Okay. Of course, how long does it take to multiply two matrices? You have two n cross n matrices using this method that we have written down. It takes n time for each element, and there are n square elements. So how long does it take? N cube. And if you have to multiply n minus 1 times, n cube times n is n to the 4. Of course, that exactly explains what we are getting. It's n to the 4. But if you look at it in terms of this, you can do it remarkably better. Okay? And here is again dynamic programming coming into play. Okay? And this is actually, let me pose the following question. If I give you, I ask you to do the following. I give you a number, little number, just a number, A. And I would like you to write a piece of code that takes as input number A and an integer n and calculates the power A to the power of n. this is a valid quiz question. Number A, power n. I would like you to write a piece of code that returns e to the n. Is the problem clear? I mean, literally, all I'm asking you to do is exponentiation. You don't have access to, of course, you have a calculator, you can write e to the n, but these are exponentiations that take n could be very large, so you cannot, you have to come up with the best algorithm you can. Write a piece of code to calculate this as fast as you can, right now. Okay? So first write any piece of code that works. Let's try to do that. Okay, so it's clear, right? Whether you can write a recursive code, you can write whatever you want. So the number a is an integer, n is the a is fixed. You're just multiplying a by itself, and you're running, express your running time in terms of the number of multiplications that your algorithm does as a function of n. So if n equals 1, how many multiplications will you do? Well, 0, because you're just returning a. But as n grows, your number of multiplications will grow. Okay. Is the problem clear? Just
Can they be together? Can they be
no. That's a good question. So a could be anything, but let's assume it's positive. N is positive. What's the simplest piece of code that you can write? So can somebody give a simple recursive code for this? Yeah.
So power an equals to power a n divided by 2 squared.
Okay. So the simplest piece of code I would say is if n equals 0, then what do you do?
Return a.
Return 1. Else you could do power of a n minus 1 times a. Okay, so this one is doing 1 multiplication for n equals 1. You agree that this is a right piece of code? How many multiplications will this do? And in this case, n if you include the multiplication with 1. So this will do n. Okay? Good. But the point is that you can actually do faster than this. You can do it using, the idea we mentioned it, you do it using log n multiplications. Okay? You can think of it as like divide and conquer. You can also think of it as like a dynamic program. In the sense that you're saying that to get a to the power of n, one thing I can do is that actually I can get a to the power of n over 2, and I just multiply it by itself. Okay? Remember, we are counting multiplications. We are not counting multiplications of a. We're just counting multiplications. So here is the Foster algorithm. Okay, what is the Foster algorithm? The idea suggested was, I just return power of a n over 2 squared. I mean, of course, there is a problem with that because n may not be even. So what do? So you could do floor and ceiling, but then that will be a problem.
If a is not even, then you times a to that. So n minus 1 divided by 2 and n minus 1 divided by 2.
Correct. So you do, and okay. So I think everybody should try to write down this piece of code. Remember, if I write it like that, I have a problem because I'm not memoizing. You are doing this and you are separately doing this, right? So you want to do this only once and then multiply it with itself. So can people power of a n The base case is if n equal to 0, then you return 1. Otherwise, what do you do? If n is even, okay, I'll let people, can people so write a piece of code that makes sure that it only uses log n multiplications. So you want to go ahead and let's say you compute n equals power of a ceiling of n over 2. So we've already computed that. If n is even, what do you return? If n is even, you return, what do you return? M times m. If n is odd, what do you return? M squared into a. Right? M times m. How many multiplications are you doing overall? So you're doing at most 2 multiplications for every halving of n. Every time n divides by 2, you're doing at most 2 multiplications. So you're doing at most 2 times log n multiplications. You can probably do it more careful analysis, but you agree that you're only doing that means powering of a number to a power of n only takes you how much time? Log n time. Okay? Now, there's nothing special about that being a number. You agree? I could have replaced that by a matrix, and exactly the same thing would hold. And there is nothing special about the fact that we are multiplying. We could also apply this to this funny multiplication. That would be fine. That's the power of abstraction. Once you have a sort of a recipe in mind, you can apply it in many different ways. So the point about this is that calculating this can be done in log n multiplications. Log n funny multiplications. Each funny multiplication takes time n cube. So the whole thing can be completed in n cube log n time. So this all pair shortest path algorithm that we wrote down, if we just did it more carefully using the powering analysis, we can complete an n cube log n. Okay. Again, how would we do it? We would take this powering routine, we will implement that. But whenever we have a product, what do we replace that by? The funny multiplication. And what is the funny multiplication? It's exactly this, something like matrix multiplication, except we are replacing product by sum and sum by matrix. Yeah.
Is there a way to minimize the matrix multiplication itself?
Very good question. Very good question. So, is matrix multiplication, we said, takes time n cube? Okay, why can we do it faster than n cube? Or after all, you're only calculating n square elements. Now, it turns out there are much faster ways of doing matrix multiplication. Okay, there is a divide and conquer method called Strasson's multiplication that comes it down to n to the 2.5 or 3 or something like that, and then there are more recent methods using some ideas from group theory and algebra that bring it down even further. Unfortunately, those things do use the fact that we are talking about products and sums. Those do not extend to funny multiplications. Okay? because they actually use the fact that you're doing summations and adding numbers and multiplying numbers. I don't know the answer whether this multiplication with the product replaced by the sum, whether that can be done faster. It is, all pairs shortest path has been studied extensively, and there has been work on improving the running time from below to below NQ. But so far, it's only been done for special cases, and that's a wide open problem. In fact, there is a whole theory of problems for which we do not know whether we can do better than NQ. They are called sort of cubic problems, problems for which we do not know how to do better than NQ, even though the amount of information we need is only n squared, right? We only need to find, let's say we only need to care about the length of the shortest path, then the amount of information that I need is just n squared. I want this matrix which tells me for every pair what is the shortest path distance, right? That information is only of size n squared. And the input I'm giving is also of size n squared. Do I really need to spend time NQ? It's widely open. We do not know the answer to that. Okay. However, notice that we have not yet arrived there. Our running time is what? NQ log n. So you could ask, can I get rid of the log n? Okay. And here is really a beautiful algorithm that actually, a different algorithm, a different dynamic program that brings it down to NQ. Okay. It just looks at the problem slightly differently, and you will see and in some sense I feel it's an easier so we have covered this so far. We will look at this Floyd-Warshall algorithm. To me it seems like actually an easier dynamic program. Okay, so in this dynamic, so remember in a dynamic program, we were talking about here shortest paths from I to j, and then we added this variable k, which represents number of hops. Okay, because we were trying to figure out what if the shortest path from I to j, what was the previous hop that was there, and that number of hops keeps going down. So we have this order in which we can proceed these problems. Okay, so the Floyd-Warshall idea is look at it just a little bit differently. Okay, so let me use instead of C, let me use something else. Let me use M. So let me define M I J K equals length of shortest path from I to j whose intermediate vertices are drawn from 1 okay. So there we are limiting the number of hops. Here I'm saying let me look at the shortest path from I to j. Okay, that's going from I to j, but the intermediate numbers that you can put there, the intermediate vertices that you can use there, are only allowed to be from between 1 and k. 1, 2, 3, 4. So it's not allowed to be any of the n vertices. Okay, all the vertices are being numbered 1 through n. So it could be any one of the vertices 1 through n. Okay, is the definition clear?
Yes.
So in that, let's take a quick example. Okay. So what is M261? What is M261? So it's the shortest path from 2 to 6 that can only go through vertex 1 in the middle. So that will be 3 plus 6 equals 9. What about M262? Shortest path from 2 to 6 that can only go through vertices 1 or 2. So what's the answer to that? 9. Right? What is M263? Shortest path from 2 to 6 that can go through vertices 1, 2 or 3. So you have, well, yeah, 4 plus 2 plus 6. That's an option. This is also an option, but we take the better of the two. Okay? Is the definition clear? All right. So there is a very, very simple recurrence you can write for this. Very simple recurrence to write. Okay? So let's think about it. I'm looking for the shortest path that goes from I to j, whose intermediate vertices are only allowed to be 1 through k. Agreed? So again, like in a typical recurrence, I will ask you how do I differentiate between the choices? Okay, I would like to express this in terms of, let's say, k minus 1. So I'm going to ask the question, is k part of the shortest path? I don't know, but either it is, either it's not, right? Let's say k is part of the shortest path. Okay, let's say k is okay. Let's suppose k is not part of the shortest path. Then what is the shortest path from I to j using vertices from 1 through k? It's exactly the same as the shortest path going from I to j using vertices only 1 through k minus 1. So that's one choice. So one choice for I to j is using mij k minus 1. Sorry.
And when we say that, that just means it's kind of like 1 hop from I to j?
No, any number of hops, but its intermediate vertices can only be between 1, 2, can only be drawn from the set 1, 2, 3 to k minus 1. Any number of hops. We are not placing any bounds on any hops. We are only placing constraints on what the intermediate vertices can. Okay, so for example, M263 is the shortest path from 2 to 6. It can only go through vertices 1, 2 and 3 in between, because 3 indicates the order allowed. So in this case, if you look at this path, it goes through only vertex 1. If you look at this path, this is not allowed because it goes through vertices 1 and 4. If you look at this path, this is allowed because it only goes through vertex 3. Okay. If you look at this path, that's not allowed because it goes through vertices 3 and 4. Okay. So mij k minus 1 indicates I'm looking at the shortest path from I to j using vertices 1, 2, 3 all the way till k minus 1. Okay. It doesn't have to include all of them, it can include any one of them, but those are the only ones that can go through. Okay. So this choice indicates that I'm picking a path in which I'm not taking k is not present. Okay. But remember, I'm trying to solve, I'm allowing k. So I should consider the possibility of k being present. So let's say k is being present in my shortest path from I to j using vertices 1 through k. So if k is present, then this consists of 2 paths, right? Here to here, here to here. What is this path? It's the shortest path from I to k, whose intermediate vertices are what? 1 through k minus 1. Because remember, k will only appear once, it won't appear more than once. because there are no cycles. Okay? So this is Mik, k minus 1. What is this?
Same thing.
This better be the shortest path from k to j using no more vertices only from 1 through k minus 1. So this is mkj, k minus 1. What is the length of this path? This plus this. Okay? So Mijk is the minimum of two quantities. Mijk minus 1 or Mik k minus 1 plus Mkj minus 1. Yes. What is the nice thing about this recurrence compared to the other recurrence? The nice thing about this, no, there also there were only three variables, I, j and k. And here also there are only three variables, I, j and k. But but in order to calculate one entry of this, how much time did it take? One entry, I c, I, j, k, it took n time. In order to calculate one entry, how long will this take? Just 2 units of time. Right? You just have to 3 units of time. So that's how there is the saving of n. And notice that there is no matrix multiplication or anything like that. So this will just take you n cube time. Okay? I'll just write a piece of code, which is very straightforward. Let's see about this. Okay? So the base case will be k equal to 0. When k equal to 0, intermediate vertices are not allowed. There are no intermediate vertices. So for I equal to 1 to n, for j equals 1 to n, what is Mij 0 equal to? What is the shortest path from I to j using no intermediate vertices?
Weight of ij.
The weight of the edge ij. No intermediate vertices allowed, please weight of the edge ij. Otherwise, from I equal to 1 to n, for j equals 1 to n, for k equals 1 to n, and Ijk is just the minimum of these two quantities. That's the entire algorithm. Takes input W. That's it. This is why I keep saying that once you have the recurrence, really writing that is just 4 more lines of code. You just have to add the algorithms. Okay? Good. So, and the running time of this is clearly here in Q. As always, if you wanted the shortest path, we can add a new matrix called Hij, which will keep track of the fact whether k is being included or not. If k is being included, it will say yes. If k is not being included, it will say no. And you can do your backtracking to extract the actual paths. Okay? Okay. So that's basically all pairs shortest path. So the things to keep in mind for shortest paths in general is that Dijkstra's algorithm works for positive weight, non-negative weights. It will single source. Bellman-Ford's algorithm works for negative weights. It can detect negative weight cycles. So if ever you have to find out a negative weight cycle, you can say I'm going to run Bellman-Ford and figure out a negative weight cycle. All pair shortest paths, the best way to do it we know of, but we're studying in class, is cubic running time, all pair shortest paths. So you can just refer to Floyd-Warshall algorithm, or you can just assume that it's.
What's the last line of code again? What's it?
So this is, I was saying that if you want to keep track of the shortest, if you want to keep track of the actual path, you can add a new variable hij_k.
Oh,
Okay, which will, if the minimum is obtained here, it will say, let me just write this down. So if this is the minimum, then it will make a note that hij_k is false. Okay? By that it means k is not included in the shortest path from I to j using vertices 1 through k. If this is the minimum, hij_k equals true. Okay? So then when you have to calculate the, by the way, what is the final shortest path value? What is it given by? Mij n. Because you want to find the shortest path that goes through any vertex possible. Okay? So if you want to find the actual shortest path, what would you do? If you want to find the shortest path from I to j, you look up hij_n. It will tell you whether n is included or not. Okay? If n is included, then n will be the last hop. Actually, it may not be the last one. But if n is included, n will be included. So then what do? You have to do if n is included, if hij_n is true, then what do you return as your shortest path? You look up hin n minus 1 followed by n followed by hnj n minus 1. Let me write this down. So return shortest path. From I to j. Let's say you want to return the shortest path from I to j using vertices only 1 through k. How do you figure that out? Well, you check. If hij_k is true, then what do you return? You return a concatenation of 3 things. Okay? You return the shortest path from I to k using k minus 1, followed by concatenate that with k, and then go from return from shortest path from k to j using k minus 1. Okay, this dot means concatenation. You are returning, this will give you a list of vertices, put k after that, and then after that, this will give you a list of vertices. Okay, this is the case if Hij is true. If Hij turns out to be false, that means k is not in the list, right? So what do? You return the shortest path from I to j using k minus 1. Okay, that's how we will establish. All right, I think we'll stop here. And if you have not collected your quiz 1 or quiz 2 or some of the old stuff, I still have it. Please collect it. Otherwise, everybody have a great Thanksgiving break. We'll see you